All right, it's recording. Exercise 7E. 7E is pretty much what you've done so far with 7D and 7C. The only difference is they're using function notation. So you just need to be able to read their function notation. So again, I've given you a table in case you're sort of getting a bit confused with it. The way I think of it is pretty much how I normally read transformations from a graph. So for example, back in chapter 3 when you did turning point form, if I gave you, say, 2 bracket x minus 1 squared plus 3, if I asked you now, what does the plus 3 do, what would you tell me? Up by 3, right? So this is called determining the transformation by inspection. So I'm not doing the mapping notation I taught you previously. You can do it and get the answer, but this is called by inspection because after a while you do pick up on certain patterns. So that plus 3, you said up 3. Now notice in the function notation, it's actually very similar. You see, when I say translation of k units up, which is over here, so I'm going to highlight it, k units up. Notice that plus k is exactly the same. So when you're reading by inspection, whatever I taught you over here, so if I said, what's the x minus 1 do, what would you tell me? Right by 1. So here, the way I taught you back in chapter 3 and chapter 4 was that you let it equal to 0, solve for x, if it's positive, moves to the right, 1. What you find it's interesting is that when it's minus 1, it ends up being to the right by 1, right? But if you read the function notation, notice that it's actually very similar. See, with function notation, when I say moving h units to the right, so here, h units to the right. In the mapping notation, it is plus h. But interestingly enough, it's f of x minus h, because it's what you're substituting into the function. So that's how I normally do it. So this is the sort of introduction for you to be able to read a transformation equation. As you get better at reading this, then you don't have to do the mapping notation for easy functions. Later on, there'll be complex functions to complex functions. Then the mapping notation technique I taught you for C and D is useful. But the expectation is that by the time you get to year 12, you should be able to read something like, well, sorry, not like that one, but yeah, something like that one. Or if I gave you, even if I gave you a function you haven't learnt yet, so let's say e to the x minus 1 plus 2, you should still be able to read to me what the transformations are. That's the goal. Okay, so that's the goal. That's what exercise 7E is training you to do. To start off, you get used to the function notation. Okay, but out of curiosity, anyone want to have a go with reading the transformation to this graph, even though you might not know what this graph actually looks like? Anyone take a guess on something that you might know? Up by 2. Very good. This is still, whatever the graph is, up by 2. What else?
Right by 1.
Yeah. This actually means right by 1. And it's the same kind of concept that this is the function. It's whatever you're doing to the x, just like this one. Doesn't matter about the x squared, doesn't matter about the root. It's what you're doing to the x coordinates is an x transformation. Everything else is a y transformation. So over time, as you practice C and D, you will start picking up on the patterns and you'll be able to read them quickly. Okay? So let's have a look at the table over here just so you get a bit more familiar with it. This is the mapping notation for reflection. Remember, reflection in the x-axis means the mirror is on the x-axis. So it flips vertically. That's why it's on the negative on the y. Reflection on the y-axis means the mirror is on the y-axis. So if it had to be symmetrical, it flips horizontally. Hence, negative is on the x. Dilation, what's another word for dilation? Stretch. Very good. So you either stretch horizontally or you stretch vertically. Now, as I'm moving my hands this way, this hopefully helps you remember from which axes we're talking about. So when I say dilation of factor A from the y-axis, so think about the y-axis, I'm moving away from. So what values am I multiplying to? Is it the x or the y? The x. Okay, so hence why I wrote a times x there. Okay, so it's just getting used to reading the transformation. So this is what you did 7D and C. Over here, we're doing exactly the same thing. So notice where the negative is. The negative is on the y. And so negative is on the function. And if you're wondering why that is true, well, think about it. If you're putting a negative on the y, so I'm replacing, normally it's y equals f of x. If it's negative on the y, when you divide both sides by negative, you get that. Whereas this one, this is negative on the x. Can you see it is a negative on the x? Literally. Okay, and this process to go from here to here, if you wanted to see it, you actually have to do the mapping notation I taught you beforehand. You would say this is x dash is equal to negative of original x. Rearrange to get original x, and that's how they resubstituted this into the function. So if you're wondering why is this x plus h and then ends up being x minus h, the reason why is because you're saying new x is equal to old x plus h. You rearrange that so that you can replace the old x to get the new transformation. So here, minus h on both sides. And that's pretty much why I tell you guys to let it equal to 0. This is where I was trying to sort of dilute it down so that it's easier for you to understand, but not really understand. Yeah, so that's where I came up with the idea to make it equal to 0. Yeah, so that x minus h is where that comes from. So they take this, what you learned from 7C and 7D, and they put it there. So what are you learning in 7E? To read this transformation. One of the most common ones that students make a mistake with is the dilation. So here, when you times it by a, it ends up being timesing by the reciprocal. It actually ends up being times by 1 on a. Yeah? Whereas the y, anything to do with the y doesn't change. See, b times y, there's my b. B's still here. And if you want to know y again, same thing. If you let that equal to y dash equals by, and you rearrange it to find y, you'll find that original y equals y dash on b. Put it over here, so then move the b across. That's why they times b on both sides. That's how it happens. Okay? So that's all they did. They just replaced this here, and you actually end up with y dash on b is equal to f of x. That's how they got bf of x. That's where it comes from. Okay? So everything you learned from C and D, you can technically apply here to find out how they got this. Okay? Otherwise, if everything I just described was too confusing, memorize it. Okay? So that's another way. You can just memorize that. Over time, you get really used to reading function notation. Cool? All right, let's do an example now. So that's the theory. Let's do an example so that you get sort of a feel of it. Example 1, 2, and I think I've got another one on the back. Yep, 3. Let's do example 1. I'm just going to delete this now. Here we go. Example 1. Let's read the question. It says, a transformation is defined by, they tell you what the transformation is. You have to be able to read this now. Okay, so out of curiosity, Artie, what's that transformation? How do you read that? What's that 1/3 mean? Good. Dilation of factor 1 on 3, and the key one is from? No, it's from the y. Okay, and that's the confusing part. So just be careful when you're writing your answers because it does matter. So in a SAC, I would penalize you if you put an x there. Yeah. So you're multiplying the x values. So think about stretch along the x-axis. Then you can see it's moving away from the y-axis. Okay, so that's dilation of factor 1/3 from the y. Let's try the next one. What about this 2y? Let's go with Ben. Actually, were you here the last 2 sessions? No. Oh yeah? Go. Very good. Dilation factor 2 from the x-axis. Okay, and again, you're multiplying the y values. So if you move your hands, you can see I'm moving away from the x-axis and I'm doubling it. Okay? Now it says find the equation of the image if the graph is y equals x squared plus 2x plus 3. Exactly the way we did in 7C and 7D. This is original y, that's original x. This is your transformation. So we do the same thing again. We say, all right, well, this is your new x is equivalent to 1/3 times the original x. Whereas this one is saying that New y will be the result of doubling the original y. If you want to get the new equation, you need to replace the original y and original x. I need to rearrange these equations to find out, well, what's original y equal to, and what does original x equal to? So here, how do I get x by itself? I don't need this third. How do I get rid of the third? What would you do? Divided by both sides. So that's one way, or in my case, because the symbol there is divide 3, I would have just times 3 to both sides, but both techniques work. So you can actually do divide by a third. Divide by a third is just a lot of students aren't comfortable with number on a fraction. Okay, so one of the ways I tell students to do it is I say, if that's a fraction there, do the opposite, times by the reciprocal, and you times by the reciprocal. 3 divided by 3 cancels out. And you end up with original x is equal to 3 times new x. On this side, this is easier. What's original y equal to? Let's go see on. What's original y going to equal to?
New y divided by 2.
Beautiful. New y divided by 2. Now I've got them both. Then we look at this and we say, all right, so now the old y is equivalent to y dash on 2. So I replace it. I say, okay, so this is now y dash on 2. That's the original x. Original x over there is 3x dash, and I'm squaring it, plus 2 times 3x dash plus 3. Okay, so I'm literally just replacing all the old x's and all the old y's. And here we go. We get y dash on 2 is equal to 3x squared, just means 3x times 3x is 9x dash squared, plus 6x dash plus 3. Well, we never leave our answer without the y being the subject, so I need to get rid of that divide 2. Opposite of divide 2, times 2. So here I'd say times 2 to both sides. You've got to times every term by 2. And I get y dash is equal to 18x squared plus 12x plus 6. Now I'm putting the dashes just so that you know this is the new equation. Okay, in reality is that you don't put the dashes. You actually just write y equals 18x squared plus 12x plus 6. But if you don't put the dashes, you can get confused which one's the old, which one's the new. Yeah? So in your final answer, maybe just take off the dashes and just leave it as x and y's. Okay? So far, so good. That's pretty much revision of 7C, 7D. So or more like 7C, learning how to read the notation and then getting the new equation. Okay, so this is the old equation, and it's now transformed to this. So if you type that in, it should do exactly what you want. It should stretch or compress by a third and horizontally, and then stretch vertically by a factor of 2. Let's try the next one. Example 2. All right, example 2 is now a revision of 7D. We're going backwards now. They tell you that you started off with old x like this, and technically that is your old y. Okay, so now you have to get used to thinking in terms of function notation. That's old y, old x. This is your new y, new x. Okay, so I'm going to replace it again. I'm going to say this is your new y. Think of it like y dash. And that's your new x. Think of it like x dash. Doing what you did in exercise 7D. Now, the problem is that it's hard to read what the transformations are. So one of the techniques is when you get these two x's, one of the techniques is to make it 1x. The only technique we know is complete the square. Let's see how many of us remember how to complete the square. Who wants to have a go with the first one? X squared plus 2x. What is the completed square? Who wants to have a go? Sion.
Is it plus 1 minus 1?
Plus 1 minus 1. Yes, that's true. So you're saying x squared plus 2x plus 1 minus 1. Is that what you mean? Plus 1 minus 1? Yeah. Okay, so this here is a perfect square. That's true. That's right there. What do you do with the minus 1 and plus 6? Very good. Minus 1 plus 6 gives you positive 5. That's called completing the square. So remember, half the b term, half of this middle number will give you this. And then if you square that number, you should get the last value. But you can't just add on a number out of nowhere. That's why we subtract that number, so it never existed. This is what we started off with. So this gives us a perfect square. This is the leftover. Minus 1 plus 6 gives me plus 5. Why do I like this? Because you can read it. Up by 5, left by 1. Yeah? Now, the second one's a bit trickier. You can't just do completing the square because there's that 2. So what do you have to do? You have to factor it. There's no way around it. It means you're going to have to work with fractions. Okay? Here we go. We're going to have to take 2 out as a common factor, even though there is no common factor. If I take out 2, I will get x squared. So 2 times x squared gives you 2x squared. 2 times 4x will give me the 8x. And then 2 times what will give me 5?
512.
512. Very good. Leave it as a fraction. Don't change it to decimals, not 2.5. All right. This now, you can complete the square. Let's have a go. I'm going to keep it in color-coded so you remember the 2 is still on the outside. So doing what Sion did before, you got x squared plus 4x. If you want to know what you need as the last constant, half the speed term and then square it. So if you half 4, you get 2, and then you square it, 4. So that means you need a plus 4 and a minus 4 to make this statement true. Yeah? So here I'm going to write it again. It's x squared plus 4x. And I'm going to put in plus 4. I'm minusing 4 because it never existed. Plus 512. Well, the reason why I like that plus 4, because that is a perfect square. What would the perfect square be? What's inside the brackets? Very good. Becomes x plus 2. And if you've forgotten, it's that number there is just the result of halving 4. So half of 4 gives you the 2. Don't forget the square. That's a perfect square. And then that means I just need to work out now, in terms of fractions, what's negative 4 plus 512? Anyone want to have a go? Negative 312. Good. Quick way of doing it. 2 times 4, or 2 times negative 4 is negative 8. Negative 8 plus 5 is negative 3. Okay, so you can do it that way if you're not used to fractions. So here, 2 times negative 4 is negative 8. Negative 8 plus 5 is negative 3 on 2. Your final one now, so this is the completed square, but remember you still have a 2 on the outside, so you got to double every term. If you double every term, 2 times this bracket will give you 2 bracket x plus 2 squared, and then 2 times negative 3 on 2 should give you minus 3. So if I zoom out now, we can clearly see old y, old x, new y, new x. Now we're going to use exercise 7D to go backwards. Here we go. I'm going to use, instead of f of x and g of x, just to help you, I'm going to call this y for original y. And I'll call this y dash as new y, just so that you're a bit more used to what I'm going to do. Okay? Now, 7D, for those who haven't started doing 7D, your goal is to compare and say, what did I replace for this x to become the new x? I always start with the x's first. So the function is a square. What I'm affecting is here. This is what I'm doing to the x's. It's the x plus 1. So that means in here, where the square is, these two, is what I'm replacing. I must have replaced this x plus 1 with x dash plus 2. So these two are linked. That's the x transformation. Everything else is a y transformation. So I'm going to color all the y transformations. So this plus 5 belongs with the y. This minus 3 belongs with the y. And this 2 also belongs with the y transformation. So now you actually have to rearrange those two equations. So here we go. Let's rearrange it to make it clear. The 5 is meant to be with the y, so I'm going to minus 5 on both sides. You will get original y minus 5 is equal to x plus 1 squared. Okay, that's original x, original y. So we can see now transformation for y, transformation for x. Let's do the same thing for this one. If I plus the 3 on both sides, I will get y dash plus 3. And then to get rid of that 2, I need to divide both sides by 2. So, in one step, this is what I get. Let me know if I've confused you anywhere. Okay, because what I'm trying to do is to compare. I've got a square, I've got a square. I've got the x transformation, I've got the x transformation. And this is my y transformation mapped with my y transformation. This is Xi7D. Okay, so if you haven't done it, this is what you need to practice. Yeah? So I'm mapping all the y transformation with the y transformation. I'm mapping all the x transformation, which is the x plus 1, and x dash plus 2. Once you've done that correctly, then from this step, what is our goal? Our goal was to find the sequence of transformations. Means you need to find what x dash is and what's y dash. Because x dash y dash tells you what you're doing to the transformation. So here, let's rewrite it. Original y minus 5 must be mapped to y dash plus 3 on 2. So I'm just connecting these two. The second one is that I'm matching x plus 1 and x dash plus 2. So I should have x plus 1 is equal to x dash plus 2. Because that's what I had to replace. From the original, what did I do to make it this? I had to replace these two. So they must equal. And same thing with the x's, these must equal. Okay? And what's our goal? Our goal is to find x dash and y dash. So what is y dash equal to? What's x dash equal to? Here we go. X dash is easy. Minus 2 on both sides. And you get x dash is equal to 1 minus 2 is negative 1. Here we go. That's what x dash equals to. Y dash. I need to get rid of that 2, that fractional 2, and that 3 afterwards. To get rid of that divide 2, opposite of divide 2 is times 2. So I'm going to times 2 to both sides. Times 2, times 2. Remember there are 2 terms here, so you have to times both of them by 2. So here that should be 2y minus 10 is equal to y dash plus 3. Minus 3 on both sides because I need the y dash. So then I get 2y minus 13 is equal to y dash. So in a nutshell, what I'm trying to say is we started off with some xy coordinate, the original xy. It's mapped to, and what we just figured out is x dash and y dash. We figured out what the transformation is. So if I fill it in, it's x minus 1 for the x dash. So there's x minus 1. What's for y dash? Y dash is 2y minus 13. Now you can read it. Now you can actually read the transformation. So let's read. Here we go. I'm just going to zoom on this side so you can see. What are my transformations? Remember, Dr. T, you have to do BODMAS, so dilation is multiplication. Reflection is also multiplication, but of negative number, and then addition, subtraction is your translation. Yeah? So Dr. T, which one comes first? Dilation. Dilation comes first. Do I have a dilation? Yes. Which one, Namafi? Good. Dilation of factor 2. Beautiful. From the x-axis, because I'm multiplying to the y values. Is there a reflection? Do I have any negative on the x or y? No. So that means now I move on to translation. Do I have any translations? Which translation can you see? Let's go with Lillian. What do you see? Translation of what? Ooh, close. When it's minus 1 there, it actually is minus 1. So in the sequence, in the mapping notation, it is true to what it is. But if it's in a function notation, it would have been f of x plus 1. Okay, so in this case here, actually means left. So translation, left by 1. Very good. Next one. What's the minus 13? Let's go with Akisha. What do you think the minus 13 could be? You're affecting the y value, so it can't go left. It has to go y value, so vertical. Down, that's right. Translation, down by 13. Very good. So that is your sequence of transformations, Dr. T. And with translation, it doesn't actually matter which one goes first. I was just going X and Y. Yeah? So you can say down 13 and left 1. Doesn't matter. Dilation should come first, though. Okay?
If it was like negative X, how do you word that one?
If it's negative X, then it would be reflection has to sit in between dilation and translation. So you'd say reflection. Now, to affect the X, you have to flip horizontally. So there'll be a reflection in the Y-axis. Okay, so the Y-axis is the mirror. So instead of saying reflection in the mirror, you'd say reflection in the, where's the mirror? It's the Y-axis. How's that feel so far? So that's a revision of 7C, 7D. So far, so good. The only difference here is they embedded a bit of f of x and g of x. Yeah? We'll do one last example. Flip over the page. Flip over the page. One last example for today, and you can do the very last one yourself. It's a problem-solving one. All right, so now that we've revised 7C, 7D, this one, I want you to use the table if you're not used to reading the table. Part A. Example 3 says f of x equals to x squared. That's equivalent to you saying y equals to x squared. So you have to get used to function notation. They say here, part A, write the equation for the graph of y equals 4 times f of x plus 3. What does that mean? Well, f of x plus 3, what that means is substitute x plus 3 into your function. So let's write it out clearly. F of x plus 3, what does that mean? If we sub it in, what you should get is x plus 3 squared. But then I say 4 times whatever that is. So since this is equal to f of x plus 3, if you write 4 in front of it, it just means, in the next step, when I say 4 f of x plus 3, that just means 4 times that. See, in the previous questions, this is what they gave to you. Instead of saying at the start, instead of doing y equals to 4x plus 2 squared, they're trying to get you used to reading 4f of x plus 3, because that's what it means. It means exactly the same things. Yeah? That could help you to understand what you need to do. This one, you're meant to be able to read the transformation. So when I look at that, I can already say left by 3, dilation of factor 4 from the x-axis. That's the speed that you want to get to eventually. But if you don't know, convert it to what you're familiar with, old x and old y's, and then you can work backwards. Yeah? So you're starting off. F of x equals x squared. This is the transformation graph. Now what they say in the next step is give a sequence of transformations that takes the graph of y equals f of x. So what are they trying to say? They're trying to say this is your original y, original x. Yeah, so f of x is this. F of x equals x squared. So this is original y, original x. And they want you to transform it to this new graph. I'm going to highlight it first. Yes, Molly.
Is it 2 or 3? Is it 3 or 2?
Oh, sorry. Thank you. That's right. It was meant to be a 3. Yes. Okay, so they're saying move from the original graph. So this is your original y, original x. And they want you to move that graph to, and if you can read this function notation, great, you would have got the sequence already. But if you can't, this is how you do it. You'd rewrite it. It means y dash is equal to 4 bracket x plus 3 squared with a dash. That's essentially what this line is saying. This line is saying take this graph to this graph. Old x, old y, to new x, new y. So that's exercise 7D. What I'm doing today is 7E, which is getting you a bit more familiar with that notation. So if you're familiar with it, you don't actually have to do mapping notation. You can actually just read it and say left by 3, stretch, vertical stretch by factor 4, right? But if you can't do that yet without the table and all that, then here you can use 7D to figure it out. So let's do 7D. Again, here's my last time to do 7D for you to sort of revise. We want to match what we see. That's a square, that's a square. What am I doing to the x? This is what I'm doing to the x. This is where x is. This is where x is. These two map to each other. Everything else must be a y transformation. So this is my y. This 4 belongs with y dash. This is my y. So in order to match it, I need to bring this 4 back with the y dash. So here, let's rearrange it. This means y dash on 4, because I have to divide both sides by 4, will equal to x dash plus 3 squared. So now I've got something squared, and then on this side, I also have something squared. Now I can do a comparison. I can say, oh, what I've done here is clearly I replaced the old y with this one. So they match. These two match. Old y equals to y dash on 4. Old x must equal to x dash plus 3. So if you match that, this is what we should get. Let's write out the equation. So old x is equal to x dash plus 3. The other one is old y equals to y dash on 4. Your goal is to find the sequence of transformations, means find x dash y dash. So here, if I rearrange it, x dash must equal to x minus 3. Y dash times both sides by 4 is 4y. Exactly the way I just taught you just now. If you wrote out the mapping notation, it was original x, original y, has transformed through a sequence to get x dash, y dash. You already found x dash and you just found y dash. You put it in and you can read it. So I put it back in. It's x minus 3, 4y. So I'll zoom out just so you can see the whole steps. Now if I ask you to read it, see x, when I subtract 3 means I'm moving to the left 3. Here, that's a dilation of factor 4, but I'm affecting the y values, so it's away from the x-axis. But I knew that from the beginning already, just by reading the function notation. So the skill in 7E is that you don't have to do this to get there. Ideally, you could just read it right there. But if you can't, then 7D, that was the skill for 7D. Okay, and 7C was the other way. 7C was like moving forward. Okay, hopefully that gives you a direction of where you want to improve on, what you need to practice. I'm going to stop there. Example 4, you can have a go if you like, but it's a bit more problem solving. So make sure C and D is good first before you try E. Okay, so E is a function notation language. Yeah? All right, I'm going to stop the video there.